Okay, so this is one of the harder questions to explain because you guys haven't seen this particular device in real life. I'm hoping a lot of you guys can make it next Saturday because I'll have this here and we can actually do the experiment hands-on. Um, but basically the way that this works is I have this hollow tube right here, and running through the middle of the hollow tube is a string. So there's nothing that holds the string in there except like it's just running through the middle. And what happens is if you swing this around in a circle, you can get to the point where the this object is held in place in the circle by the force of tension of this mass pulling down. And if you swing faster, then as this thing tries to go in a straight line, it's going to increase tension and pull big M upwards. And if you go slower, then big M starts winning the tug of war and pulling it in closer and closer. So basically, we have little m swinging around in circles and big M right there. So from there, I have all this other stuff and some numbers in there that I'll use in a sec. But what's really important for us is to recognize, first off, this is a circular motion problem. And that means, very simply, it's forces. And so we need to start with some free body diagrams. So for M, the free body diagram is going to be capital MG. And then there's going to be some force of tension upwards. And the problem says that it's going at a constant speed. It says that it's hanging in place. That means that we know that this must have a sum of forces of 0 acting on it. Then up here, the free body diagram for this guy, I'm going to draw this arced line right here because I want to be able to show really well that it has a force of tension acting on it, but that force of tension is acting towards the center of the circle. So I usually draw kind of an arced line there, similar to what you guys saw me do with the inclined plane problems, just to help give a little bit more context to my free body diagram. So there's my free body diagrams. And from there, I can go to some force equations. If I'm talking about for the mass m force equation, I'm going to have acceleration that equals the sum of the forces over m. But the only force acting on it is the force of tension. This is lowercase m. And the type of acceleration that it has is a centripetal acceleration because it's moving in a circle at a constant speed. So I can actually get a lot of information there. And then for big M, I can write a force equation, but I know that the sum of the forces is 0. So then I can say that I actually know that force of tension is equal to mg. And that's convenient because that means that I can go back up to here and say, okay, v squared over r is equal to mg over m. As long as, oops, I need to be careful here. This needs to be capital MG because I'm talking about this object, which means this also has to be capital MG. So I can't just cancel those m's because they are different masses. So from there, I have most of the problem done. I'm trying to figure out what m is. So let's get m by itself. That would involve multiplying both sides by little m, dividing both sides by g, and I just get v squared over m, oops, I'm sorry, v squared times m all over g times r. And that equals capital M. So it would be nice if I could just plug numbers in. I know little m is 0.10 kilograms, so that's pretty nice. I know r is equal to 0.35 meters, so that's nice. But what I don't know, the information that hasn't been given, I know g, acceleration due to gravity, is 10 meters per second, but v is a question mark. So to figure out v, I'm going to have to actually use some extra physics. I know that velocity is the change in position over time. And I know that this thing's moving in a circle, which means its change in position is 2 pi r over time. It's also making 10 rotations. So when I plug my numbers in here, I would just do 2 times pi times r, which is 0.35. But then it's doing 10 rotations in 25 seconds. So really the time for one rotation is 2.5 seconds. This is how you would do it if you're doing an experiment, because 2.5 seconds is pretty quick and there's a lot of timing error there. So doing 10 rotations, counting them out, and then dividing by 10 will get you a more accurate result. So from there, I can find out that the velocity is 0.88 meters per second. So that goes up here, 0.88 meters per second, which means now I can just plug everything into that equation, and I find out that m equals 0.22 kilograms. So that is how you do that problem. Again, if it went too fast for you, watch it again, pause it on the steps you didn't understand, and just take it as bite-sized pieces. You're in control of the whole video here. I hope that helps. Otherwise, if you're really feeling lost, please come to the tutorial, and I'm happy to help you out. All right, have a great night. Thanks.